Okay, so tonight we're going to work on some new ideas, finish up capacitance, and work on resistors and resistance. So just to review, okay, that's a little thick. Let's maybe do that a little bit better. Okay, so we defined capacitance. C is Q over V. And the idea here is that we can store charge at a particular voltage, and our sort of default idea is we have these parallel plate capacitors that have some charge on the top and some equal charge on the bottom, and so there's some voltage across them, and we have a symbol for our capacitor that looks like this, and that's supposed to make you think of the parallel plates. Sometimes we draw them like that. Okay, so that's a capacitor. It stores charge and it stores energy. And for a parallel plate capacitor, we can write that the capacitance is epsilon naught A over D, where A is the area of the plate, A, and this is D, the separation. Okay, so there are a few other things that we learned. We learned about series capacitors. And they have the same charge. So we could write, a series capacitor pair like this. So this is C1, this is C2, and we often want to replace them with an equivalent single capacitor, which has the same charge. We'll call that CEQ. And we can write that 1 over CEQ is 1 over C1 plus 1 over C2, or generally 1 over CEQ. For series capacitors is the sum of the reciprocals. And you did that in lab or are doing it in lab. Okay, so that's series capacitors. Parallel capacitors have the same voltage on them. And so we write them, so the picture looks something like this. Right, so C1, C2, and the same voltage difference across them because they're connected to the top and at the bottom. And the equivalent capacitance, we replace them with CEQ is just C1 plus C2, or CEQ is the sum of the capacitors. So, we just have some kind of nice ideas here. There are just a couple other things with capacitors that we want to talk about. So we could ask, first of all, how can we make a capacitor bigger? How do we make big capacitors? Well, it's pretty hard to make them bigger by making a bigger area or maybe making the D smaller. So you have to do something else. So if you go back to the definition of the capacitance, right, it's Q over V. If you could lower the V, so lower V for same Q, you could get a bigger capacitance. So one way you could do that is if you think about my parallel plates again, and here I'm going to draw them sort of edge on, right? So, we've got some electric field in here. because the top plate we said was positive. So that's E, right? Plus, 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 minus, 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 minus. Okay. And that gives you this, potential difference. If we could find a material, and we can find such materials called dielectric materials, they can be polarized. Oops. That is the E is lowered. The V is lowered. So the C is increased. So if we come over here and we say, well, let's do the same thing on the right here. So let me put a dielectric in. So this is with a dielectric. So you can say, well, I still have my plates, same geometry, let's say. Except now what I'm going to do is I'm going to put this material in here, block of this dielectric material. Okay, and it's supposed to fill the block. And so let's imagine that it's polarizable. So it's not conducting, but it can be polarized. So let's say that we have our plus charge here on the top, just like before, minus charge, just like before. Exactly the same, except now this material polarizes, so it develops a little bit of polarization, separation of charge. Like so. So now all of a sudden, those field lines don't get through anymore. Right? So the E is lowered, so the dielectric has the effect of raising the capacitance. And its ability to be polarized is characterized by a dielectric constant. That tells you how well it does this. And the dielectric constant is kappa. So we can use this kappa to calculate a new capacitance. For a capacitor with a dielectric, the C would be kappa epsilon naught A over D, and kappa is typically greater than or equal to 1. So the better the dielectric, the bigger the kappa. So that's a beautiful thing. You can just find some material that has the right properties and you can put it in there and it raises the capacitance. Now, it's not perfect because there's also a dielectric strength, which is sort of the maximum E field before what we call dielectric breakdown. So that dielectric breakdown is that dielectric material can't sustain those fields anymore and it becomes conducting, right? So we see dielectric breakdown all the time in the summer in the Midwest. That's what lightning is. It's dielectric breakdown. The air loses its insulating capacity between the cloud base and the ground, and bang, that's dielectric breakdown. So you can't just, kind of put the dielectric into your capacitor and crank it up forever. At some point, it breaks. Okay, so that's dielectrics. And all we're really doing is we're putting a kappa in front of that epsilon naught, right, like that. This is why I might add I always like to keep the epsilon naught around, because I know wherever the epsilon naught is, I'll put a kappa in front of it when I have a dielectric. Okay, last thing that I want to talk about for capacitors is energy storage. So we can write that the energy stored in a capacitor is 1/2 CV squared. And since we know that, that C is Q over V, or V is Q over C, we could write this as, or 1/2 Q squared over C. And that's just a simple substitution for V, right? Just put that in and you get that. So there's no new physics here, right? These are the same expression, just written differently. So that's the energy storage in a capacitor. So if you really want to store a lot of energy in your capacitor, you really want to put it up at high voltage. And you probably want to have a dielectric that allows you to have a big capacitance and a high voltage. Okay. The last thing is you could ask, where is the energy? And the answer is in the E field. So the field itself has an energy density. So we can say that the energy density in an E field, the field itself, that'll be UE is 1/2 epsilon naught E squared, where E is the magnetic field. And this is really an energy density. It's joules per cubic meter. So if you know the field, you can figure out how much energy is in the field itself. And at some point, if you have a big enough field, like all kinds of wild things can happen if the field gets to be too large. So, okay, so that kind of ends this discussion of capacitance. We have series and parallel, we have dielectrics, and we have energy storage and energy density. We used another thing in this experiment we did, which we should really now talk about. So I want to talk about the next topic, which is Ohm's law and resistance. We use devices that we called resistors, and resistors are devices that resist current flow. So you imagine a device, and that's our symbol for resistor. And we put a voltage difference across it. So we say, well, there's some voltage difference that we apply. So this is plus and this is minus, okay? And we do that, we apply a voltage difference. And what that's going to do is it's like a pressure, and it's going to drive a current through the resistor. So V, or delta V, is like a pressure that drives a current, and the resistor resists current flowing through it. Now there's a relationship, an empirical relationship called Ohm's law. Relates voltage, resistance, and current. And Ohm's law is V equals IR. So V is the voltage difference. I is the electric current. And R is the resistance. Okay, so V is in volts, and current is in amps, and the resistance is in a unit of ohms. Okay, and 1 ohm is 1 volt per amp. And we use a symbol for an ohm. The symbol we use is the omega. So we can make a nice little graph that's, kind of a nice thing. If we make a graph of a device that follows Ohm's law, we can make the voltage across the resistor, the current through the resistor, and this will be this beautiful straight line. And the slope is the resistance. And we're going to actually do that in lab in the upcoming week. And it's actually a beautiful experiment. It's one of the straightest lines you'll find anywhere. V equals IR, right? V equals IR. Okay. So you could also say that the resistance, right, is dV di, which is just the slope. Okay, so one of the things that's interesting is we talk about Ohm's law, we use it all the time. There are devices known as non-ohmic devices. Don't follow Ohm's law. And these non-ohmic devices like LED or an incandescent bulb are very interesting. They can have very interesting properties that we like. So not every device is ohmic. Our resistor are ohmic. And so we use as a symbol, that's our resistor symbol. Now, one of the things that what we should think about with resistors is, well, if they're resisting, they're kind of like a friction. They're actually going to convert electric energy into heat. And we can talk about the power dissipated as heat in a resistor goes as I squared R, or V squared over R. And again, these are the same thing with V equals IR. So it's not really a new expression, either I squared R or V squared over R. And that's the power, and that's in watts, right? Which are joules per second. So that's the rate at which heat is being produced in a resistor. So if you want a lot of heat, actually what you do is you want a lot of current. So like your toaster or your hair dryer use a lot of current because they're trying to generate a lot of heat, or one of those electric heaters that you use to keep your feet warm. They are typically high current devices because you want lots of current for some resistance. So this idea of power more generally, in a circuit is just the current times the voltage for the device. So if you know the current and the voltage across the device, you can figure out how much power it's using. So resistors are an obvious case for that. We can do things with resistors like we did with capacitors. we can put them in series and parallel. So let's talk about a series resistors. So the idea here is we want to do this. We have a resistor and a resistor. So, R1, R2, and series resistors have the same current. So remember, series capacitors have the same charge. Series resistors have the same current. So there's some replacement resistor, equivalent resistor we'd like to have, which will have the same current. So this is an equivalent resistor. And we're going to replace R1 and R2 with R equivalent. So we can say, well, they have different voltages. They have the same current, right? So we can say that the voltage across 1 is I1 R1, and the voltage across 2 is I2, or excuse me, the same I, we should do that already, same IR2. So the voltage across the pair, V, is V1 plus V2, and that's going to be equal to I times R1 plus I times R2. So that's the voltage across the pair, V. Same voltage here. So I R1 plus I R2 must be equal to the same current REQ, or REQ equals R1 plus R2. Okay, so we can write that for series resistors, R equivalent is R1 plus R2, or R equivalent is the sum of the resistances. That is, series resistors add. What about parallel resistors? Well, parallel resistors have the same voltage. So this is going to look kind of familiar. So we know that V is I1 R1. They won't have the same current. And V is I2 R2, right? They have different currents, right? There's a I1 and a I2 there, let's say. Okay. So our equivalent has to carry the total current. So the total current here, must be equal to the sum of the currents on the left, I1 plus I2, because you have some current going in here and going out here, and it's got to look the same, I and I here. So I could then say, well, okay, this must be, V over R1 plus V over R2 is V over R EQ, and lo and behold, 1 over Req is 1 over R1 plus 1 over R2, or parallel resistors add one over Req is the sum of the reciprocals. So let me highlight that. Okay. So notice that they're the opposite of the capacitors. The resistors are the opposite of the capacitors, how they act. Okay. So now we have resistors, we have capacitors. We should probably add a few more components. We should probably add, oops, I'm gonna go back to actually writing. How about that? Okay. We want to talk about EMFs. These are voltage sources, like a battery. And EMF stands for electromotive force. But it's really just a voltage difference, like a battery. And we write an EMF, or a battery, as a long side and a short side. That's our battery. Plus side, minus side. Sometimes you'll see them drawn with multiple plates, but it's always this pattern of short and long. Plus side, minus side. Okay. And we label these perfect batteries as the voltage difference like the voltage on a battery, voltage difference E. So now we could actually build a circuit So how are we going to build our circuit? Well, let's have a battery, some perfect wires, and a resistor. There's a circuit. Actually, simplest circuit you could have. So the battery has an EMF, the resistance has a resistor R, and we might want to find the current. So the voltage difference across the resistor is the full voltage of the EMF. So we could say, well, the EMF must be equal to I, R, or the current through the resistor is E over R. And you have just done your first circuit. A resistor, an EMF or a battery, and a current. Okay. So I think I'm going to stop there because the next thing I want to do is circuit diagrams. So I want to let's do a little review just to sort of summarize. Always a good thing to summarize. So summary. So what did we talk about? We talked about dielectrics. Can, or do, I should say, not can, raise the capacitance by lowering V for the same Q. And this is polarization. Shields the E. And there's a dielectric constant. Kappa describes this process. So for a capacitor that has a dielectric in it, it would become kappa epsilon naught A over D, and this is a cap with dielectric. Okay, so some other things we can say. We can talk about the energy stored in a capacitor, 1/2 CV squared, or 1/2 Q squared over C. Nothing new, they're the same. And the energy density is 1/2 epsilon naught E squared. Energy's in the field. Okay, so then we added resistors, and we talked about Ohm's law. V equals IR, R in ohms. And that's a nice linear relationship between voltage, current, and resistance. Okay. We have a symbol for a resistor. And series resistors have the same current, and they add R equivalent is the sum of the resistances. Parallel resistors have the same voltage, and they add as reciprocals let's write that carefully. And then finally, we did talk about power as heat. Power is I squared R, or V squared over R. And we talked about voltage sources, EMFs. And this is the symbol we use for them. These are basically supposed to make you think of a battery, and the voltage across it is E. That's the voltage across your battery, and it's the electromotive force. And you can put it all together in our first circuit. Voila. So we're ready to build some more complicated circuits, which I might add is everyone's favorite part of the course. So that's a good place to stop. We did about 33 minutes, which is more than enough. And I don't know if I'll get you one on Friday because I'm traveling on Friday. Notice also I put up a homework assignment that is potentials and capacitors. It's on the Mattermost, and you can go ahead and get started on that. And we got a good start on resistors, so we'll be ready for lab. Okay, and I'll talk to you all soon. Bye.